This video is going to go over examples for how to sketch the graph of a function analytically. Before we jump into the examples, let's remind ourselves of the steps we need to take for this curve sketching. First, we need to identify our domain, make sure we know what part of the real line we are working with when we are sketching this graph. Then we'll find our y-intercept. That just gives us kind of a nice point we know will be on our graph. We'll then find f prime of x and f double prime. We need those second derivatives for steps 4 and 5, where we determine the intervals where the function is increasing and decreasing, finding relative extrema, and step 5 where we figure out where it's concave up and concave down and find any inflection points. Step 6, we will find any asymptotes that we may have, vertical, horizontal, or slant, and then we'll put everything together and draw a sketch. I've listed the 4 examples below that we will go through in this video. Our first example, y equals x plus 2 cosine x, restricted to the interval 0 to 2 pi. All right, our first step is to identify the domain. And as we look at this, x plus 2 cosine x, there's nothing that is going to cause an issue there. I don't have any places where this graph will be undefined or anything like that, because my x and cosine x function both behave pretty nicely. So my domain is all reals, technically, but I've restricted to my just the interval 0 to 2 pi. So we're just going to look at 0 to 2 pi. And we don't have to exclude anything in that interval. All right, step 2, we're going to look for a y-intercept. And remember, to find our y-intercept, we let x equal 0. So y equals 0 plus 2 times the cosine of 0. Well, cosine of 0 is 1, so that's just 2. So our y-intercept is the point 0, 2. All right, step 3, we're going to find our derivatives. So we need our first and our second derivative. I'm going to use y prime and y double prime as my notation here, since my original function was given to me as as y. Since it wasn't given to me as f, I won't use f prime of x or f double prime of x. All right, so y prime, we'll take that derivative up there, and we'll get 1 plus 2 times the negative sine of x, or a better way to write this, 1 minus 2 sine x. And y double prime will be negative 2 cosine x. So I found both of my derivatives. And those are kind of nice derivatives. They didn't require a whole lot of cleaning up or factoring or anything. They're kind of in a nice shape to begin with. All right. Step 4, we're going to do our increasing, decreasing, and relative extrema. So to remember to do this increasing and decreasing, we'll need the first derivative, and we'll take that first derivative and we need to find any critical points of the first derivative. So critical points come from two possible places, either where they make that first derivative equal to 0 or where they make that first derivative undefined. So y prime, we'll check where it's undefined first. And I'm looking up there, remember, at y prime is 1 minus 2 sine x. That is never undefined. So I don't get any critical points from this function being undefined. But now we'll set y prime equal to 0. So 1 minus 2 sine x equals 0. That gives me that 1 equals 2 sine x, or that sine x is a half. And now we want to consider, where is our sine function equal to a half? Also remembering that we've been asked only to look at the domain 0 to 2 pi. All right, so where is sine x equal to 1/2 in that interval? And that's going to be at pi over 6 and at 5 pi over 6. Those are the angles for which our sine value is 1/2. So those are our critical points. All right, so now that we have our critical points, we will do our increasing and decreasing test. So remember, when we do this, we will draw ourselves a line, and we'll put all of our critical points on it. So remember, it doesn't matter how you space these out necessarily. What matters is you have them in order from least to greatest. And because I know that I'm only looking from 0 to 2 pi, I'm going to restrict the ends as 0 and 2 pi to make sure I don't go outside of that interval while I do my test. Okay, so now I need to do my test. I need to pick something in each interval. So maybe here I'll pick f prime of maybe pi over 12. That's between 0 and pi over 6. Remember, I'm testing each one of these in the derivative. F prime of something between pi over 6 and 5 pi over 6, I'll choose pi over 4. And then between 5 pi over 6 and 2 pi, I'll choose pi. Remember, you can choose anything in that interval, in those intervals, but it's usually best to pick kind of the easiest number possible in those intervals. So what do? I plug each one of these into the derivative, the first derivative, and see whether it's positive or negative, and that will tell me whether I'm increasing or decreasing. So if I take pi over 12 and plug it in, 1 minus, so I'm plugging in up here to 1 minus 2 sine of x, 1 minus 2 times the sine of pi over 12. If I plug that in, I'll get a positive number, and I'll be increasing. Okay. If I plug in pi over 4, 1 minus 2 times the sine of pi over 4, I will be decreasing. And if I plug in a pi, I'll have 1 minus 2 sine of pi, and that will be positive, so I'm increasing. So we'll write out what I was doing each time just to help as well. And 1 minus 2 sine pi over 12. Okay, so we checked each one of those, and this is where our function is increasing and decreasing. And now we need to check to see, does this have any relative extrema? Well, remember, relative extrema are going to happen if you're increasing and then turn around and start decreasing, you're going to have a relative max. If you're decreasing and turn around and start increasing, you're going to have a relative min. So I can see that I'm going to have a relative max here at pi over 6 because I went up and then turned around and went down. And then at 5 pi over 6, I'm going to have a relative min because I went down and turned around and came back up. So let's write that down. I have relative min at 5 pi over 6. And I need the y value that goes with 5 pi over 6. So the way I'll do that is I plug back into my very original function back to the very top. So up there, x plus 2 cosine x. So it would be, we need f, oh, I wrote that in the wrong spot, excuse me, f of 5 pi over 6. So that's back to the original. So this ends up being 5 pi over 6. And then if you plug it in, you get 5 pi over 6 minus the square root of 3. And just as some help later when we start graphing this, this is approximately 2.62 comma 0.89. That'll help us place it on the graph. And then we have a relative max at, so I can see that I go up and then turn around and come down. So I have a relative max right here at pi over 6. So that's at pi over 6. And then we plug into the original. So that's pi over 6, pi over 6 plus the square root of 3. And if you're to approximate that, that would be 0.56 comma 2.25. And now in general, the answers I want from you are the exact answers. So when I'm saying the exact answers, you know, I'm wanting this and this. I want the exact answers. However, those decimal approximations will help you more accurately kind of estimate where it should go on the graph. Okay. All right, so I've done my increasing and decreasing, and I've done my relative extrema. So now I need to do my next step. So we'll come back up here to the top of the page. My next step is going to be the concave up, or the concavity in the inflection points. So remember, to do the concavity and the inflection points, I need my second derivative. So y double prime was negative 2 cosine x. All right, and I want to see where is this y double prime undefined. And it's never undefined because that cosine function is one of our nice functions. And where does y double prime equal 0? Well, this is when negative 2 cosine x is 0. So this is when the cosine function is 0. And when does that happen? Well, my possible inflection points, remember, those are sort of like the critical points of the second derivative, but I just kind of call them possible inflection points because they might end up being inflection points. What do I get? x equals pi over 2 and 3 pi over 2. Those are the spots where my cosine equals 0 on my original interval that I've been given. All right, so up next I need to test. So I'll draw my interval. Remembering that I only need to look from 0 to 2 pi, so I don't want to jump outside of that interval. And I'll put my other 2 points on here, pi over 2 and 3 pi over 2, to test around them. So what values do I want to test? So I'll test these in f double prime, or the second derivative. Maybe I'll choose pi over 4 here. This middle interval, I'll choose pi. That's a nice one between those two. And then this last one, it's got to be between 3 pi over 2 and 2 pi. So that's down around to that fourth quadrant. I'm just going to choose 7 pi over 4. I like the over 4 ones better than the over 3 and 6. They're a little easier for me to remember, but it doesn't really matter. Anything on that interval is going to work. So we'll test each one of these into our second derivative. If we plug pi over 4 into our second derivative, so remember that means we're coming back up here, negative 2 times the cosine of pi over 4. So negative 2 cosine pi over 4. If we do that, we're going to get a negative number, so we're concave down. All right, if I plug in a pi, so that's negative 2 cosine of pi, that's going to be a positive number. Remember, the cosine of pi is negative 1, so that's like negative 2 times negative 1. So we get a positive number, and we're concave up. And then if we plug in 7 pi over 4, so negative 2 cosine of 7 pi over 4. So that's like negative 2 times the cosine of 7 pi over 4 is a positive number. So I end up with a negative overall, and we're concave down on that interval. So do we have any inflection points? So let's check. It looks like I'm going to have an inflection point at pi over 2 because, look, I'm concave down, and then I switch to concave up. So I'm going to have an inflection point at pi over 2. And at 3 pi over 2 because I was concave up and I switched to concave down. So I have an inflection point at 3 pi over 2 as well. So inflection point at pi over 2, comma, and now I need to plug pi over 2 into the original. So if I do that, pi over 2 into the original f of pi over 2, I get pi over 2, comma, pi over 2. Okay. And then if we want to help for an approximation later, that's like 1.57-ish, comma 1.57-ish. And then we also have one at 3 pi over 2, and then we plug that back into the very original. And again, once we do that, we get 3 pi over 2, comma 3 pi over 2, which as an approximation is like 4.7, comma 4.7. And remember, the important ones here, the actual answers, are these that I've highlighted. Okay, the ones I've highlighted are the exact answers of the inflection points, but right under them I have the approximations, which is going to help me visualize where they are on the graph that I'm going to draw in just a moment. All right, so we got a little bit more to go. Step 6, we're going to do asymptotes. This function is going to have no horizontal asymptote, no vertical asymptote, and no slant asymptote, so it's kind of quick there. And then now for the very last step, we're going to put everything together and graph. So what I like to do is to draw one big number line that has everything from the increasing, decreasing, and from the concavity testing all on one number line to help me sketch. So I do know that I'm only looking from 0 to 2 pi, so I'm going to put those on the end. My important points, my critical points and my possible inflection points, let's see what I had. I had pi over 6 and 5 pi over 6. Let's scroll back up here, and pi over 2 and 3 pi over 2. So I have quite a few. I need to put them all on there in order from least to greatest. So pi over 6 is the smallest of those, then pi over 2, then 5 pi over 6, and then 3 pi over 2. And remember, this is where we draw our pieces that show what's going on both in increasing, decreasing wise and related to the concavity. So I'm going to do my increasing and decreasing first, kind of make a little note. So from 0 to pi over 6, I am increasing. I'm looking back over here at this chart right now. From pi over 6 to 5 pi over 6, I'm decreasing. So those are both decreasing. And then after 5 pi over 6, I'm increasing. And then now I'm going to look at my concavity chart. So up until pi over 2, I'm concave down. Between pi over 2 and 3 pi over 2, I'm concave up. And then I'm concave down from 3 pi over 2 to 2 pi. So what I've done is kind of drawn both of those together so that then I can figure out like what part it looks like. So if I'm increasing in concave down, my function sort of looks like that. And now I'm decreasing in concave down. So it'll kind of look like that. Decreasing in concave up, increasing in concave up, and then increasing in concave down. So remember, what we're going to do is take each one of these pieces and sort of stretch them out-ish and to fit into my graph. So let's graph this. All right. Let me draw. Before you draw your axes, it's kind of nice to take a look at what points you have. So as I'm looking around, my min and max, I see like 2.6-ish and 0.89, 0.56, and 2.5. My inflection points, I'm seeing, 1.5-ish, 4.7 or so. So I'm kind of getting a feel for what y values and x values I might need. I know that my interval was restricted just to 0 to 2 pi, so I know I only have to use those for my x's. And then my y's, I have, looks like I'm getting, 4.7 is about the biggest I see, but I want to check just a minute, make sure I know what happens at my endpoint. So if you do have endpoints, it's nice to also know what those values are. So if I plug in a 0 to my original, I'm going to get a 2 back, and we did that earlier and found that intercept. If you plug in a 2 pi to the very original, you're going to end up with 2 pi plus 2. And just as an idea, this is 2 pi, and then comma, 2 pi plus 2 is about 8.28, just as a frame of reference when you start sketching this. Okay, so let's draw. So my x-axis and my y-axis, and let's plot out some points. I know I need to go to 2 pi, so let's handle our x-axis here. And then my y-axis, I see that like 8.28, that 2 pi plus 2 is about as high as I go. So I will make sure I get up to there. So let's say maybe 1, 2, 3, 4, 5, 6, 7, 8. And there's some markings on my y-axis. All right, so I'm going to start out. I'm going to make sure I plot all my important points. So 0, 2 was the y-intercept, and it was the end of my interval. 2 pi, 8.28-ish was the end of my interval, so I plot that as well. I'll plot my extrema now. 5 pi over 6 and was a relative min. So let's plot that one about where it should go. So what do we get? 5 pi over 6 is just less than pi. It needs to go up 0.89. So about right there seems appropriate. And then, oops, that was 5. Okay, no, that was right. And then pi over 6, comma, pi over 6 plus 3, square root of 3. That's about pi over 6, comma, 2.25 as a reference there. Pi over 6 is going to be really skinny. 2.25 is going to be about right there. So there's those points. And then let's also make sure we have our inflection points. We see pi over 2, comma, pi over 2 was one of our inflection points. So pi over 2 is about 1.5. So we'll estimate that. Pi over 2, about 1.5. There's an inflection point. And then 3 pi over 2, comma, 3 pi over 2. And we know we rounded, that's about 4.7 to give us an idea. So 3 pi over 2 and about 4.7. So notice what I've done is I plotted all my important points, and now I'm just going to play connect the dots with them in the using those shapes I just came up with. All right, so from 0 to pi over 6, I need to look like that. And that looks kind of reasonable because that's right there. And then from pi over 6 to pi over 2, I needed to decrease and be concave down. That fits nicely. Pi over 2 to 5 pi over 6. So this was 5 pi over 6. And this was pi over 6. I need to be decreasing concave up. From 5 pi over 6 to 3 pi over 2, I need to be increasing in concave up. And then from 3 pi over 2 to 2 pi, I need to be increasing in concave down. So there we go. There's an approximate sketch of that curve.